Hello, everyone. Welcome to the Module 5 of the Risk Assessment course, which is about data management and interpretation. This is Yu from the University of Minnesota, and in this module, we will explore how to effectively manage and interpret data with a focus on applications in emerging technology risk assessment. In this session, we have three main learning objectives. First, we will identify key databases and tools used for hazard identification and exposure assessment in mixture risk assessment. Second, we will evaluate how to combine multiple data sources to address data gaps and better characterize risks in emerging technologies, including additive manufacturing and nanotechnology. Finally, we will apply the mixture risk assessment framework to real-world scenarios, demonstrating how databases and tools can be used in practice. This slide highlights three key databases that support mixture risk assessment. First, the Agency for Toxic Substances and Disease Registry, ATSDR, provides minimal risk levels for acute, intermediate, and chronic exposures. These values cover both inhalation and oral routes and focus on general environmental exposure. In emerging technologies, they are often used to assess chronic low-dose exposures such as nanoparticle emissions or VOCs from additive manufacturing resins. For example, we might use them to evaluate long-term exposure to ultrafine titanium dioxide in a nanomaterial production facility. Next, the NIOSH recommended exposure limits include occupational exposure limits for a variety of chemicals, including nanomaterials. They often provide nanomaterial-specific values, such as for carbon nanotubes or ultrafine titanium dioxide. These limits help evaluate workplace hazards from additive manufacturing, metal powders, or nanoaerosols, such as determining safe exposure limits for graphene nanoplatelets in research lab. Then the EPA's Integrated Risk Information System, IRIS, provides reference concentrations and reference doses for multiple exposure routes. This database supports dose response modeling and cumulative risk assessments, particularly when occupational limits are not available. For instance, we could use IRIS to determine inhalation reference concentrations for aerosolized polymer powders in a production environment. The American Conference of Governmental Industrial Hygienists, ACGIH, threshold limit values include TLVs, short-term exposure limits, STELs, and biological exposure indices, BEI, updated regularly based on toxicological studies. These limits differentiate different chronic and acute exposures, making them useful for quantifying additive risks from volatile emissions in both 3D printing and nanotechnology environments. For example, we might compare the TLV TWA for styrene exposure in SLA 3D printing operations. OSHA permissible exposure limits set legally enforceable workplace exposure limits and often serve as the baseline compliance criteria. In emerging technologies, they are used to ensure that additive manufacturing and nanotechnology processes meet regulatory standards, such as verifying that silicon nanoparticle exposures remain below OSHA limits. Finally, the European Chemical Agency REACH database contains derived no-effect levels and risk management recommendations for chemicals regulated in Europe. This resource is especially valuable when US-based oils are unavailable. For instance, DNLs from REACH can guide assessments of polymer and solvent toxicity in binder jetting additive manufacturing. Here we see how we can apply these databases in practice for emerging technologies. First, we can compare multiple exposure limits. For example, by combining NIOSH RELs with ATSDR minimal risk levels, we can determine if nanoparticle emissions exceed cumulative exposure thresholds. Second, we can assess multi-route exposures. This could mean combining EPA iris reference concentrations for inhalation with ACGIH biological exposure indices to track systemic absorption of nanoparticles through biological monitoring. Finally, we can address data gaps for novel materials. One example is using ECA-rich derived no effect levels alongside Stoffen Manager Nano to estimate nano-specific exposure risks when occupational exposure limits are unavailable. In this case study, we have an industrial facility using selective laser sintering, or SLS, with polymer powders. Workers in this facility are exposed to three main hazards. First, ultrafine polymer particles, for which no established occupational exposure limits currently exist. Second, acetone, a solvent used for post-processing tasks. And third, ozone emissions that result from laser interactions during the printing process. This combination of exposures make it a suitable example for applying mixture risk assessment principles, especially when exposure limits may be missing for some materials. In the first step of the mixture risk assessment process, we focus on exposure assessment. For this case, exposure data were evaluated using tools such as Stoffen Manager Nano, the occupational exposure banding process, and TLV and REL data. The findings show that ultrafine polymer particles were assigned to band E, indicating the highest risk category. Acetone exposure levels were measured close to its TLV of 500 parts per million. Meanwhile, ozone exposure was found to fluctuate near its TLV of 0.1 parts per million. These results highlight that all three hazards require careful consideration in the mixture risk assessment. In the second step of the mixture risk assessment, we focus on the dose-response relationship. For this case, we use STM 2.0, NIOSH roll data, and ACGIH TLVs to identify appropriate health-based limits. Since no established OELs exist for ultrafine polymer particles, default precautionary limits were applied. For acetone and ozone, established TLVs and PELs were used where available. This step ensures that such substance in the mixture has a defined benchmark to compare against measured or estimated exposures. In the final step of the mixture risk assessment, we characterize and prioritize the identified risk. Using control banding, in combination with STM 2.0, we evaluated the combined systemic and inhalation hazards from all agents in the process. The analysis showed a cumulative exposure hazard index greater than 1, indicating potential concern. In addition, several agents were operating near their regulatory limits, which triggered a red flag for future control measures. This step integrates all prior data to determine which risks require the most urgent attention. In the final stage of our case study, we focus on risk management, where the goal is to recommend effective control measures based on the findings from the earlier assessment steps. Using the CB Nano tool and control banding, we identified targeted strategies to reduce exposure. These include using enclosed printers equipped with HEPA filters to capture airborne particles, installing local exhaust ventilation in post-processing areas, and requiring appropriate respiratory protection such as P100 or powered air purifying respirators during cleaning and powder handling tasks. These measures ensure that cumulative risks from multiple agents minimized, keeping workers' exposures well below regulatory and precautionary limits. In this case study, the assessment identified ultrafine polymer particles, such as engineered nanoparticles, as the controlling compound. This determination was made for three main reasons. There are no established occupation exposure limits, such as no-ILs, low-ILs, or reference doses. The particles fall into the highest hazard band, band E, according to both Stoffen Manager Nano and the CB Nano 2. Workers face frequent and poorly controlled exposures during post-processing tasks. The risk analysis showed that the mixture risk index exceeds 1 based on outputs from STM 2.0 and the CB Nano 2. This indicates an unacceptable cumulative risk when considering combined exposures from ultrafine particles, acetone, and ozone. This assessment identified inhalation as the primary exposure pathway, particularly during post-processing activities such as sanding and cleaning, where urban particles and vapors can be generated. Dermal exposure was a secondary concern, occurring mainly during handling of uncured resins. To address these risks, several control measures are recommended. First, improve local exhaust ventilation during post-processing. Second, install enclosed 3D printings with HEPA filters. Third, provide appropriate respiratory protection such as P100 or powered air purifying respirators during cleanup. Fourth, strengthen training and supervision to ensure proper control use. Fifth, consider substituting current resins or binders with alternatives that have a lower hazard potential.
This lesson has been created by the Interdisciplinary Training, Education, and Research Activities for Assessing and Controlling Contaminants from Emerging Technologies program, a collaboration of the University of Minnesota School of Public Health, the University of Iowa College of Public Health, and the University of California, Los Angeles Fielding School of Public Health. Funding for InTERACCT is provided by the National Institute of Environmental Health Sciences of the National Institutes of Health. The content of this lesson is the sole responsibility of the developers and does not necessarily represent the official views of the National Institutes of Health.